Welcome to the session 3 on mobile lab product design. In the first session, we discussed about the concept or idea and the need. Second session, we have discussed about the specifications and the design part, at least the block diagram part. In the third session, we will be designing about, or we are discussing about the prototyping part. We have built a prototype board, we have tested. What is the concept here? That is the base board and the piggyback board that I will be discussing. Whatever the specifications I have listed out, and I represented with the help of some components and the blocks, how they have converted into a base board and the piggyback board. That is what I am going to discuss. And maybe in the fourth session, I will show you the working by loading some software. So in short, what we are trying to avoid is a separate DC power supply, a digital storage oscilloscope, a function generator, a logic analyzer. These are the major test and measuring equipment. Of course, for arbitrary function generator, we are trying to avoid. And also the possible components, right? Possible resources like LEDs, LCD, 7-segment display, switches, push to on switches, sockets. How to get rid of this soldering part, right? The zero PCB where you have to solder it some small circuits. So we want to avoid that. No need of this typical soldering. Okay. So we used to do mini projects by using such type of zero PCBs by mounting those components and soldering them. Those things also can be avoided because on the baseboard itself we have provided good number of IC sockets, components, as well as breadboard. All right, so let's see how this baseboard is designed. Okay. Before I will show you the actual system, let me brief you about various sections of the board. To begin with, the power section, that's the most important. Before you mount any components, right? Before you mount any components, any of these electronic components, you are supposed to verify the short circuits of the PCB. By any chance, while manufacturing the PCB, while fabricating the PCB, there is a possibility of short circuits. If signals are short circuited, there is no major issue. But if the power is short circuited, then there is a serious nature of problem. It is a serious nature of problem because, and you are also going to use the SMD components, and the tracks are drawn below the ICs. So once you mount the component, it is very difficult to trace where is the short circuit. So you are not supposed to mount any of these components. Just make sure, though we are giving a fabricated PCB, which consists of a lot of components, but make sure first give the power to the board, or if you have a multimeter, just check the continuity between the power supply and ground. There should not be any short circuit. So how to give the power to the board? As I mentioned, you can see A 0 to 18 volts AC. So this is, you can see my cursor, this is one input. I will show you how the power supply looks like. So from the power supply, you are supposed to connect 0 to 18 volts AC supply here, 2-pin socket, right? A 2-pin socket, screwed socket, I will show you that you are supposed to insert it here. do not touch the wires, only hold the plastic part and insert into this socket. There is another socket, that is this thing. The difference between this and this is 2-pin socket and this is a 3-pin socket. 3-pin socket is 18 volts AC. So connect this connector here. Then the board, this entire board will get 0 to 18 volts AC here and 18 volts AC here. Okay. So, I mean, we are trying to derive the desired voltages of DC from the AC supply. So, the input is 0 to 18 volts AC, here 18 volts AC, but rest of the voltages, what are the rest of the voltages? Plus 15, minus 15, plus 5 volts, plus 3.3 volts. All these voltages were trying to derive from these two sources. Okay. Then there is another way of giving the power, that is, as you can see, there is a USB connector here which is connected to the microcontroller itself. There is a separate board like a piggyback board. We purposefully kept this as optional because there is a possibility of changing the microcontroller. Today we are using X microcontroller. Tomorrow you prefer to go for Y microcontroller. Rest of the board will be same because these things are not going to change. Your signal conditioning, your power supply, your sockets, your displays, they are going to remain same. In future, if at all, if you come across some latest CPU, even a better communication device, then just in this socket you have to replace it. So that's why even this CPU also we kept it as an optional piggyback sort of a choice. All right. So the third source of power, that is 5 volts, you can give it through this USB connector. So please note, there are three ways we are giving the power. Direct DC, if you want to give 5 volts, you can give it through USB here. Otherwise, from AC mains, if you are operating, we are providing you an adapter. The adapter output is 0 to 18 volts AC here, 2-pin, and 18 volts AC here, that is 3-pin. So these are the A, B, C. These are the three main sources of the power to the entire board, including your piggyback boards. Okay. Uh, we have not mounted here. There is another optional way of giving the DC power. So it's a choice. We didn't mount here. Through USB, not using the computers or laptops power. If you want to give a DC 5 volts by using some adapter, then you can mount it that USB connector here. So this we didn't do it. We are giving the power from this 0 18 volts and 18 volts for this entire board. Okay. So how this AC supply, once you give it, is converted into DC. The moment if you give the power, there is a LED which will be which is there on the CPU will start blinking. So that is one indication that the board is powered up. And if there is a LCD is mounted here, we will provide the LCD. If it is LCD is mounted here, even the LCD will be powered up. That's an indication that the board is getting power. But otherwise, if you have a multimeter, as you can see, there is a 5 volts connector here and ground pin here. Between ground and 5 volts, right, if you put the probes, it will show 5 volts. Otherwise, this piggyback connector, there is a 1 here and 2 here. In these pins also, we have provided plus 5, plus 15, minus 15, 3.3 volts pins. So enough number of pins, VCC pins and grounds are here. You can measure those voltages by using your multimeter. Okay, because see, before we demonstrate the functionality of the board, which is replacing your power supply, DSO, and the function generator, logic analyzer, first you have to make sure the board is intact, the board doesn't form any short circuits, and the board is properly powered up. Okay. And whenever you are mounting the components, right, any of your digital components here or piggyback boards over here on this connector, make sure the power is off. please remember, in electronics, the load means current. So you are not supposed to suddenly apply the load on a when the power is given to the system, right? I mean, it is applicable to any electrical systems, isn't it? You are supposed to switch it off and change the load and again give the power. So from where this AC to DC conversion is happening? Though it is not a matter of concern for you because it's already designed, well designed board, but just for information, as you can see, this regulator, you can see here, there is a regulator where the mouse is moving. 0 to 15 volts variable DC is, this IC is taking care of providing variable DC. That is called LM317. Then there is another regulator called 7915, which is providing a constant minus 15 volts DC. Then 7815, which is a regulator for providing plus 15 volts DC. So that is taken care by this. And then you have a plus 5 volts DC supply, which is supported by this 7805 regulator. We are deriving plus 3.3 volts from this regulator, that is LM1117, which will give you 3.3 volts. So as you can see, 0 to 15 volts variable DC by this LM317, constant minus 15 by 7915, constant plus 15 by 7815, plus 5 volts is coming from 7805, 3.3 volts is coming from LM1117. So these are the various regulators which are used, which will, though the input may be much higher, right? Maybe you are providing 18 volts and so on, because your AC is 18 volts, but the output is as per the specifications. So it is regulating and it's providing a constant DC. And as you can see, filters are there, a good number of, you can see filters are there, 2000 microfarad capacitors, 100 microfarad capacitors, and there is a tiny capacitors of 0.1 microfarad, what is called decoupling capacitors. So they will take care of any kind of AC ripples which will be filtered out, and they will provide you a constant DC. Not only that, while operating the circuit, whenever a switching is taking place between VCC and ground, the supply is going to be polluted. So that's why you will notice so many these capacitors are there, this brown colored one, not the black one. The brown colored capacitors are mounted very close to the supply lines of the VCC because we want to maintain the constant DC. So that is one of the most important requirement whenever you design the power. You might have noticed why some of the tracks are thick, some of the tracks are thin, is because of this reason that based on your load requirement, you have to take care of the thickness of the tracks, that how much current is passing through the tracks, accordingly the thickness, right, the cross-sectional area you have to take care. Also, since the input is AC, you need to convert into DC first before filtering. As you can see, there is a rectifier. There is a bridge rectifier here, and there is another bridge rectifier here by using the diodes, right? So this is our, as what you can see is that this entire section is called power supply section. As good as we have replaced the traditional heavyweight power supply by using these components. Okay, so that's the source for that. As I said, without power, no electronic component works because finally it is a flow of electrons. Okay, then the other part of this baseboard is the resources. What are the resources we have on the board? The simplest thing is the sockets. You can see there is a 20-pin socket here, another socket here, third socket here, fourth socket here, and there is a 8-pin socket here. You have 5 sockets where any component you can insert into this, and the pins are brought it out here. These 2 pins are actually shorted. So either you can connect it here or you can connect it here. For example, if you are interested in pin number 1, So pin number 1 is available here as well as here. So anywhere you can use it. So by using these male-female connectors where we will be providing, you can make the circuit complete. For example, if this pin, if you want to connect it here, then we will provide you male-to-male pins. So one pin you connected here, another pin you connected here, as good as this particular pin is connected to this particular pin. So no need of soldering here. Just by using male-male, male-female, female-female jumper wires, you can complete the circuit and reconfigurable. Your circuit you can redesign by simply removing these wires. But make sure whenever you are making the connections, this power, that is 018, 18018 and USB power is switched off. You have disconnected the power. Then only make the circuit or build the circuit. Another way of building the circuit is you can see breadboard. The difference is here the components could be anything. It could be IC, it could be transistor, it could be diode, it could be resistor, it could be anything. You can mount it here, right? We have pasted a small breadboard to this baseboard itself, so that a small circuit which is not possible to mount it here can be mounted here. Or externally also breadboard you can add it. That is also issued at secondary level itself, where you can build your circuit. Okay, so at least the minimum breadboard is available here to take care of a simple analog and digital components. Okay, so that is one resource we have called sockets. Some optional components we didn't mount. In future, if you want to add any more SMD components, any resistors or capacitors or inductors, you can mount it here. It is a choice. Okay, so that is one resource. What are the other resources is about the your function generator. Instead of using traditional function generator, you can see such a small tiny board is mounted here. Actually, it is soldered, right? These components can be soldered here, called digitally direct synthesis function generator, right? So what do you mean by digital? Digital means here it is programmable. This function generator, a tiny IC, is interfaced to this CPU through some SPI port, the three wire connection. So through software, you can program this function generator to generate the desired waveforms. So we will discuss more about the application in later. But so this part is replaced by function generator. Okay. So then the third part, that is oscilloscope, right, or logic analyzer. Uh, you can see there is a CPU here, RISC controller, 32-bit RISC controller, along with the Wi-Fi part. So all these signals, you can see there are pins here, there are pins here. These are already connected on these sockets. You can see there are piggyback socket 1, piggyback socket 2. They are already, these pins are brought it over here. So if you are interested in monitoring either analog signals or digital signals, they're actually captured by this CPU and communicated either through USB or Wi-Fi or Bluetooth to mobile phone or a laptop. So here your screen, right, your DSO screen, LCD screen is replaced with the help of mobile phone screen or a laptop screen or your computer screen. So we are communicating the data and we are displaying the data because it's quite natural. We are all having at least a mobile phone or maybe a PC. So the data could be plotted on those screens. In fact, a bigger screens we have. Okay. So that details the design part, software part we will deal some other session. But a DSO logic analyzer data acquisition is taken care by this CPU, which I already said is a choice. You can choose a different CPUs, but we have chosen this RISC 32-bit ESP32. Okay, there are several reasons for that. As I said, finally we have to look at who is our customer, what are the skills, right? In a first year itself, if you wish a student should be able to program a CPU, a student is not aware of the architecture, a student is not aware of the embedded C programming, student is not aware of the peripherals, then we are supposed to choose a CPU which is user friendly in nature and then the compiler is also a scripting language rather than a hardcore C language. That is the one of the reason why we have gone for Arduino based CPU or Arduino compatible CPU. And as I said, we have some other requirements like wireless communication, multiple ADCs, multiple DACs, multiple GPIOs, and good amount of memory, high-speed computation. So we have to look at all these aspects while choosing this CPU. All right. So this is the heart of the system, because this is the one which is acquiring the data and communicating the data, and of course equally responsible for display of the data. I said display of the data because on the board itself we have provided a LCD connector. I didn't mount purposefully because once we mount this LCD, then these components won't be visible, right? They will be on top of it. So there is a LCD connector. You can connect different types of LCDs. Text LCDs also different types, 16 by 2, 16 by 4 or 20 by 2 and so on. So we are providing 16 by 2, but you can change if you want. Similarly, graphics LCD, you can solder it here, which works on a I2C protocol. Now, again, graphics LCD are different types, touch type and a simple graphics type. 64 by 128 resolutions are available. So it's a choice, you can interface the LCD. But this LCD is nothing to do with your mobile phone or a computer, because this LCD is directly connected to your CPU. So you can write a program, device driver program, to display the data on this LCD. So as good as you are, a small multimeter or a display you have on board to visualize some parameters on the screen. All right, so this is another resource. Then since these components may require a clock without using function generator, we have provided a 555 clock source, right? This IC is not mounted, but however, as you can see these components, you can vary the frequency by adjusting this potentiometer, port 6. So this port 6 screw is multi-turn port. By rotating this knob, you can change the clock frequency of this 555 IC. So that clock source could be input to various these digital components. The clock output is available not only on the pins, but it is also available on these sockets, so that even the piggyback boards also can make use of this clock. As you can see, V clock, that's available here. However, that is as I mentioned, T6, but otherwise also it is available on the sockets, so that the piggyback board, if requires the clock source, it can make use of this 555 clock, right? Which is a, I mean, you can adjust the frequency by adjusting this port number 6. The other resources are maybe any electronic, I mean, laboratory requires switches, on-off switches, DAP switches. Both the sides it is open, and now it is your choice where you want to connect. Whenever you want to make or break the circuit, you can make use of the DAP switch. Similarly, LEDs. Instead of LED, we have used a bar graph. There are, you can see 10 LEDs here, another 10 LEDs here. One is common anode configuration we have used, another common cathode configuration we have used, so that in common anode configuration, the anodes, all the anodes of the LEDs are connected directly to the power, that is VCC. So only you have to connect the cathode part, that is this, to your output of any of these electronic components. So means whenever you give a 0 volts, this LED will be on. If you give 1, LED will be off. Or if you don't connect anything, even then LED is off. So that's the meaning of common anode. However, common cathode is exactly opposite, where all the cathodes of these LEDs are grounded, already grounded. So you have anodes are floating. So whenever anode, if you give a 5 volts, right, because at least you should give minimum 3.3 volts. So if you give somewhere around 3.3 volts to 5 volts, then you know, we have taken care of these resistors, which will limit the current. So protection is already there. That's another advantage. Generally in laboratory, it's a common practice that, you know, without using resistor, students are tempted to give the power, and the LEDs are blown off. So that is taken care here, because as you can see, this resistor package, single in line package, 330 ohms is already connected. So if you give here, since it is a common cathode, if you give 5 volts here, then the LED will be on. So from your digital components, whenever you want to monitor active high state, you give here, the LED will be on. If you are interested in active low state, then give here, the LED will be on. If you don't give any input, then both the cases, the LEDs are off. Okay, so this is, generally we monitor the digital states by using LEDs, right? We don't need even a CRO for that matter, because 10 plus 10, 20 LEDs, that means as good as 20 output states of any digital circuits we can indicate on these LEDs. The numericals, right, the BCD numbers, right, whenever you want to display, we prefer these 7 segment displays. As you can see, the 7 segments plus a decimal point, right? It's actually LED, but then, the way it is organized in such a way that you can display the numbers, 0 to 9 numbers, along with the decimal point. We have used a common cathode configuration. That means these LEDs cathodes are already connected to ground. So in the sense, if you give 5 volts, then only the LED will be forward biased. And as you can see, already the resistors are there, protection, current limiting resistors, so that you don't need to worry about the damaging of these displays, because that generally happens in the laboratories. But in our case, that is taken care, because already resistors are soldered to these LEDs. So 2 7-segment displays are there, larger in size, so that these BCD numbers from 0 to 9, or you can say 00 to 99, or the practicals where conversion of one number to other number. So those things can be verified with the help of these 7-segment displays. So this is another resource for mainly for digital and embedded systems. There are some switches are there, push to on switches. One is pull up, another is pull down. Pull up means whenever you press this switch, it is connected to VCC. The output is available here. Pull down means whenever you press the switch, the output is grounded. So that output is available here. There is another switch which is a reset of the CPU. So that reset is provided here. Whenever you want to load the program on this CPU, as you can see, there is a separate USB connector is there, which is connected to this microcontroller. So this USB is also giving the power to the CPU. So this power you connect it to your computer and write the program in Arduino compiler and download it. Once you transfer the program, right, before transferring, you are supposed to press this small button called load program, right? The software will ask you, press the load button, boot load button. So there is a switch here, please remember. If you press this switch, the tiny switch, then only program is loaded into the CPU and will start working. Working in a sense like data acquisition, communication takes place, or programming your function generator. Otherwise, if you doesn't require any CRO, if you doesn't require any function generator, then you can use these LED switches, 7-segment displays, 555 clock, and the sockets, breadboard. They doesn't require any CPU. As it is, you can use it. Although also the signal conditioning, right? This doesn't require a CPU because these are all analog components. Okay, right now I'm not discussing about the signal conditioning part. This itself is a, interesting subject. What is the need of the signal conditioning and how that is achieved? That I will discuss in a separate session. All right. So with this, I think I have discussed about what is the concept of a breadboard, and on this breadboard, what is the concept of baseboard? On this baseboard, this equipment like power supply, function generator, DSO, and logic analyzer, and of course the most common components like sockets, LEDs, 7-segment display switches, and the breadboard and optional components, 555 clock source, LCD display. So many functions we are able to provide in one system itself. That is the meaning of a mobile lab. Lot many things can be done that we will discuss it, because it's a finally a risk based 32-bit risk based system. As I said, it could be of internet of things, it could be embedded systems. We can also discuss about various sensors, that we will discuss a separate baseboard. I am not talking about IoT or embedded baseboard. There altogether we have a different kind of peripherals which are mounted on the baseboard, not only just a sockets. It will also having some sensors, or it is also having a choice of choosing microcontroller, right? Piggyback board means I want to work on ARM processor, I want to work on PIC microcontroller, I want to work on Atmel controller. So it is a choice. In embedded system, choice is the CPU. In IoT, choice is the sensors or the wireless communication. So there the baseboard concept is different. This board we are talking in the context of analog and digital electronics. That is a BW, LIC, EDC network theory. Okay, so this completes our third session of how the design is converted into a prototype board called baseboard. Okay, thank you.